Okay. Good evening, everybody. Can I get started? You can tell it's the end of the semester. I was just saying everyone's just like quiet, tired, ready for a break. So welcome to the Final Our Universe Revealed for this semester. And this evening, we are going from the large scale astronomy. We've done quite a lot of astronomy this semester. I'm going to say nuclear fusion 2 weeks ago was astronomy as well. To the small, going from the bigger scales in the universe down to the internal structures of materials, electrons, and what I like to think of as weird quantum effects. I think as any student, Richard Feynman, I think, said, if you understand quantum mechanics, you've kind of missed the point because it's completely weird and completely against our intuition. But it's my pleasure this evening to welcome Yi-Ting Hsu, who is an assistant professor in the physics department here at Notre Dame. She did her PhD at Cornell University and then was at the University of Maryland as a postdoctoral research associate before joining Notre Dame in 2020. So an interesting year to join the university. This year is a little more normal. So it's been nice to welcome our new colleagues into the university and tell us about her research. So she is a professor in condensed matter research, all things small. And let's give her a nice warm welcome as she tells us all about electrons in quantum materials. Let's give her a nice warm welcome.
Well, okay, so thank you for the introduction. And so today, what I'm gonna tell you is a story about quantum materials, okay? And this story contains three important discoveries in physics history. But before I dive into describing what those discoveries are to you, let me first use a few slides to set the stage such that you can appreciate more why those discoveries are surprising, okay? Okay, so talking about quantum materials, a good starting point would be the periodic table, okay, of chemical elements. So all these symbols here, these just represent different kinds of atoms that can exist in nature or in labs, okay? And the purpose of showing this table, this huge table, is of course not asking you to read those, okay? The purpose of showing it is really just to show you that there are tens of thousands of lots of materials, because it's not just these elements, okay? It's all different kinds of combinations of these elements can lead to different materials, and that can have very different properties. Okay, so let me give you two examples. Okay, so seemingly very similar materials can have very different properties. For instance, let us start from this Cu. This is copper. Okay, so copper is a very common metal in daily life, right? You can basically get electrical coils made of copper from Home Depot, right? But what happens is that if you pull an electron, just one electron, out of one copper atom, what happens is that it becomes a nickel. Okay, so sorry. So it becomes a nickel. So this nickel, Ni here stands for nickel. And these two materials, although it's only a difference of one electron per atom, it's very different because, well, nickel is magnetic, but copper is not. Okay, so this is one example. Another example is that let's now stop switching atom types, okay, and focus on this carbon here, okay? And if I put my carbon atoms in this complicated three-dimensional structures, it becomes a diamond, okay? But if I put it into these two-dimensional planes, it becomes graphite. And if I only look at one of these planes, okay, so if I put these carbon atoms into these hexagonal shape, it becomes the so-called graphene. And although they're all made by carbon atoms, these materials are very different, okay? So for instance, although the graphene and graphite, they conduct electricity, diamond does not. And even if you look at these two, they're both electric conductors, but if you try to quantify them using numbers, okay, using conductivity, which is a number that quantifies how easy it is that you can push electrons through the material. Okay, so if you look at that number, conductivity, then you see even these two have very different numbers. Okay, and showing these two examples is just to show you that material properties are actually very sensitive to all the details. Okay, it's the atom type, and it's also the geometries and all that. So this is actually very formidable because as a person who wants to understand the properties of all these materials, there are so many of them. And if there's no simple rule that I can try to connect, to try to relate them and try to understand their behaviors, it sounds like the only way I can go about it is to look at them one by one. Okay, there's no other way around. I can only look at them one by one. And because there are so many of them, if I'm gonna do it that way, it's gonna cost a humongous amount of time and effort and money, right? So that sounds a little desperate, but it's too early to be desperate, okay? So for physicists who are interested in materials, complicated material systems, what we do in a main part of our research, basically, is to identify the common features among all those different materials. Okay, and obviously, in reality, those common features are way less obvious than just the colors, right? That you can see from by eyes, right? But it's usually way less obvious. Okay, and then the next thing that we want to do after identifying these common features is to understand why. So why are they all red? Why are these all magnetic? Why are these all conducting electricity? So these are the questions that we're interested in. And we want to find the answer at a microscopic scale, okay? And at the level of how electrons behave. And for instance, these are all red, perhaps because these are electrons, okay? These electrons are red themselves, okay? Or it's probably because they're all wearing red hats. Okay, so at that level, okay, so don't take it literally, right? And right, so this is sort of the logic that we condensed matter physicists go about this kind of problem, okay? And the thing that I want to emphasize here is that we usually become extra alert when we see that there is a universally common feature or even just a number, okay, that's seen in a huge group of very different materials. Because if you see such a universal quantity or a common feature, it usually means that the electrons are doing something interesting, okay? So we'll pay extra attention to that kind of cases. Okay, so today in the rest of my talk, what I'm gonna do is I'm gonna give you such a famous example, okay? And so the story starts in 19th century. Okay, so this Edwin Hall was an American physicist, and he was doing his PhD at Johns Hopkins. Okay, and then he did this experiment. What he did was that he took a gold leaf. Okay, but it turns out that any metal or semiconductor thin films will work. Okay, so he took a gold leaf, although this is not gold, and what he did was he applied an electric current to it. Okay, so what an electric current does is that it's pushing electrons into the sample, into this gold leaf in this y direction, okay, this longitudinal direction. Okay, and I'm gonna call this electric current IY because it's in the y direction. Okay, and then what he did is he applied a magnetic field that's piercing through this gold leaf. Okay, and although it's really piercing through this sample, but just for presentation purpose, let me move that arrow to the side, okay? And what's gonna happen? What the magnetic field is gonna do to the electron is the following, okay? This current is pushing electrons going in this longitudinal y direction, but this magnetic field is pushing the electron sideways. okay, it's deflecting electrons to this x direction. And this is called a Lorentz force, okay? And so what happens is the following. Okay, so after a while, fine, you get a pile of electrons on one side, but not the other. Okay, so this is the so-called Hall effect. And this is the famous discovery by Edwin Hall. So this is the first discovery. Okay? And a way to quantify this Hall effect, okay, with numbers is now you look at this voltage difference between this edge and this edge in this transverse direction, okay? Because there are a bunch of charges here, but there are no charges here. So there's gonna be a voltage difference, okay? And it's meaningful. It's a meaningful quantity to look at. The ratio between this voltage difference Vx and this current Iy, okay? So let's quantify this effect using this ratio. This is called a transverse resistance. And let me label it as R Hall resistance, okay? And the reason why we want to look at this ratio is inspired by the Ohm's law. So for audience who have heard of Ohm's law, it's saying that the voltage is really a product of the current times the resistance. Here, we're sort of borrow this concept because now my voltage and my current are in different directions, okay? But still, we want to look at the ratio of it to quantify quantify this Hall effect, okay? And what Hall also did was that he increased the magnitude of the B field, of the magnetic field. And then he saw that this Hall resistance, which measures how the strength of this effect, basically, it grows, okay? And so graphically, this is what happens. You can imagine this line to be, all the data points, lots of points that Hall took, the data points that at which magnetic field strength, what are the Hall resistance and so on, okay? And so he saw that this Hall resistance, that ratio, grows linearly with the magnetic field strength, okay? And more importantly, this growing rate, okay, depends on which material you're looking at. He started out with gold leaf, okay? And what I meant was that if now you change another material, it's gonna still linearly grow with the magnetic field, but with a different rate. This one grows a little slower, and then perhaps you change to another material, it grows a little faster. So that's what I mean, okay? So this rate is material dependent. Okay, so now let me emphasize one thing. That is, this experiment was done at room temperature because, well, back then it's you probably can't do it at a very low temperature, right? So at back then, Hall did it at the room temperature. I'm emphasizing this because I want to contrast this experiment to an experiment that was done 100 years later. Okay, so let's fast forward 100 years later. So in 1980, okay, so Klaus von Klitzing, this is a German physicist. What he did was he cooled the environment down to this very, very, very low temperature. That's close to absolute zero. And what he did the same experiment all over again. It's just at a very low temperature. And the reason why he wanted to do this is because, when the temperature is high, there are all these thermal noise, thermal fluctuations. But when you're at very low temperature, you don't have those. And so the quantum effect will be evident. Okay, so that's sort of the motivation why we wanted to go to a very low temperature. Okay, so now again, he did the same experiment. He pushed the electrons using the current in the longitudinal y direction. And then he measured whether there's any voltage drop in the transverse x direction. And he looked at the ratio of them, ratio of this voltage difference in x and the current in y. And look at the Hall resistance, basically, and how this Hall resistance changed with the strength of B field. So basically, he repeated what Hall did. Now, the result is pretty surprising. it's very different. Okay, so instead of growing linearly with magnetic field, now you see these steps, right? So it's very different. And this won him a Nobel Prize 5 years later. Okay, so then now you see, I'm calling it quantized Hall effect. Actually, I didn't call it. This is quoted from the Nobel Prize website. Okay, so I haven't explained to you why these steps are called quantized Hall effect, but I will later. Okay, but let me first put the two experiments at different temperatures side by side, and so that we can compare them. Okay. Okay. So besides the obvious difference that one is growing linearly, but the other is having steps, another difference that I want to emphasize is that remember that how the growing rate depends on material. So here in this room temperature case, the Hall resistance is material dependent. Okay, but in this case, it's universal, meaning that as long as you're looking at two-dimensional metal or semiconductors, as long as you're looking at those, it doesn't really depend on which material you're looking at. You're always gonna get this curve, okay? And specifically, I mean these plateaus, these steps, okay? And here I want to get a little technical because this is important. That what's surprising is that all these different materials are getting the same Hall resistance with this expression. So what does this expression mean? First, let's look at this part. There are some weird symbols, right? So this E is the electron charge, and this H is the Planck constant. So it doesn't matter for what those are for our purpose. You just have to remember that it's really just a number coming from the so-called fundamental constants. Okay, so when you see this expression H over E squared, it's really just 25,812,000 ohm. Okay, so it's really just this number. Okay, so roughly 26,000 ohms. Okay, and then how about this first part? Okay, so this C here, it's always integers. Okay, so for instance, if you look at this first step, it's C equals to 2 because remember I said that this second part is like 26,000 ohms. If you divide it by C equals 2, you divide it by 2, then it's roughly 13,000 ohms, right? And then if you, oh, sorry, the number is so small here, but this is 0, this is 5, this is 10. So this is roughly 13, you can see. So that's what I mean, okay? So if you plug in different integers into the C, you will find, and times that 25 something something, right? And then you will find the values that these steps correspond to. Okay, so this is the so-called quantized resistance, because what quantized means is that it's an integer multiple of something. That's what quantized means. Okay, and here the C is integer times something. So that's why people say that in this case, the Hall resistance is quantized. Okay, and now let me emphasize another surprising thing. That is these numbers, okay, they are obtained very robustly across samples that's prepared in different labs. Okay, and even using different materials, as long as it's a metallic film or semiconductor film, it doesn't matter which atoms we're looking at, which materials, and the sample geometries don't matter. Okay, any shape will work. And if there are some dust in the lab, and it just happens that it drops at different locations on the sample, as long as there are not too many, that don't matter either. Okay, so this number here, these numbers, is very robust. It's the precision is 1 part in a billion. That's how robust it is. So this is the surprising part, at least to me and to many people. This is the surprising thing, that you're getting really a universal number. Actually, it's numbers Okay, that is 1 over some integer times some number. Okay. Okay, so it's so robust that it becomes a new standard unit for resistance. It's replacing ohm. Okay, because labs in different places in the world, they're all getting the same values. So it's okay. So they are using that as the new unit. Okay, so that's how robust it is. Okay, so that's the quantum Hall effect. This is how it's called because these Hall resistance are quantized, and so this effect is called the quantum version of Hall effect. Now the question is, why is the Hall resistance quantized? Meaning, why is it given by these integers, and why is it universal? This is a very natural mystery that people wanted to figure out, right? And so answering this question leads to the Nobel Prize in 2016. Okay, and I'm quoting from the website of Nobel Prize. And at first sight, you probably think that, oh, why is this related to quantum Hall at all? Because there's no such words as quantum Hall in this description. And it's just because you see here, there is a mysterious term called topological phases of matter here. And let me tell you that quantum Hall effect, samples with quantum Hall effect is the first example of such kind that physicists realized, okay? And that's why I'm saying that quantum Hall effect won, the explanation for quantum Hall effect won the 2016 Nobel Prize. Okay, so before I explain to you why we're getting those quantized values, let me use some cartoon to explain to you what topological means. Okay, so obviously this mysterious word is an adjective, right? And this is actually related to so-called topology, which is an important branch in mathematics. But today I'm definitely not gonna go into that, right? All I need to explain to you for understanding quantum Hall effect, I just need a clock. Okay, and this clock is a little different. It only has one hand. It doesn't have like 3 hands, right? And so let me explain what topological means, this adjective means, okay? So view this as a definition. This is just the way we define it, okay? So let me describe a situation that is not topological, okay? So now you see there is a person who's carrying a clock with only one hand. And then he's walking around this park, okay? So now, as he walks this person walks from here to here, you see that the hand of the clock rotated a little bit, right? And then the person keeps walking, and you can see that the hand wiggles a little, but not too much, okay? And then finally, the person got back, okay? So this is the situation where it's not topological because that hand didn't move a lot. It's only wiggling locally a little bit. Now, let me show you a situation where it is topological, okay? So now the same person is carrying a clock. Now he walks from here to here. You see that the hand rotates from North Pole to here, pointing to the right. And the person keeps walking. Now it rotates another 90 degrees. And then to the 10 o'clock direction, and then back. So although the beginning and the end, this clock looks exactly the same, but we saw the process. This hand actually rotates for once. It winds once, okay? So this is the case where we say it's topological because that our hand winds around once. Okay, so now you see that pattern, okay? So another example that is also topological is when you have to pay attention to where it's pointing to, okay? And then now it rotates, it rotates back. And then it rotates down again. And then in the end, it's back. Okay, so during that journey, that clock rotates for twice. It winds twice. Okay, so this is also topological. So as long as it winds more than once, it's topological. Okay, so as long as it winds integer times, it's called topological. That's my definition. Okay, that's actually people's definition. Okay, now how is that related to quantum Hall at all? Okay, so let's come back to the quantum Hall effect. Okay, so now it's not just people who can carry clocks. Electrons can carry clocks too. Okay, this clock is called a phase. Okay, and what I'm going to tell you about this phase is just that this clock is just that where it points to depends on the electron's momentum. Okay, and also whether there is a magnetic field in the environment. Okay, so this clock, where it points to depends on these two things for our purpose. And using this electrons clock, one can explain what happens in the quantum Hall effect. Why is that Hall resistance quantized integer times integer multiple of something? And why is it universal? And the physicists who did this explanation are these four gentlemen. And let's call it T, K, and N. Okay, and they did that explanation. They managed to explain it 2 years after the experiments were done. So I think that's amazing. Yeah, and so this is what they did. Of course, this is such a complicated subject, so I'm going to only tell you an aspect of it. Okay, and then I'm probably gonna skipping a lot of things, but the gist is the following. Okay. So let's start from position space. That's just the space that we live in. Okay? And then there are electrons. And electrons can have different momentum, meaning they can move in different directions with different speed, right? And with this, I can go to a dual space, a mysterious space that's called a momentum space. But actually, it's not very mysterious. All I'm doing is really reorganizing these electrons with different momenta onto this space. So for instance, this electron moving at momentum P1, I'm gonna put it here. And then this electron moving at P2, I'm gonna put it here. And the P3 one is gonna be put here. So that's all I mean. I'm reorganizing these electrons into according to the momentum that they carry. That's all I'm doing, okay? Now, remember the Hall experiment? It was with this sample, I'm pushing through a current in longitudinal direction, but then I'm measuring the voltage difference in the transverse direction, and I'm looking at this ratio between the voltage drop and the current, that's the Hall resistance, right? So what TKN, those people did, is that they showed that this quantity can be actually simply understood in the momentum space. This quantity, this Hall resistance, boils down to the motion of the clock of electrons when going around this loop. And this is just because you see in the real space, in this normal space, we're interested in understanding the motion of electrons in this direction and also this direction, right? And that boils down to in the momentum space. I care about all the electrons along this momentum loop, okay? Now, let's focus on this dual space, okay? And then let's first look at the simple case where there is no magnetic field, okay? Now, I have a bunch of electrons living in this space, but we only care about the one that's around this loop. And let's focus on in which direction the hand of the clock is pointing in. Okay, so let's start from this guy. Okay, it's pointing upward, and then it wiggles a little, but in the end, as I go back, it didn't change a lot. It's not winding. It's not winding along this path, right? So in this case, it's not topological, according to our definition of that person who's walking around the park, right? Now, what happens if I turn on the turn on the magnetic field? What happens is that if you focus on where the hand is pointing in, you see now it rotates by once as you go around that yellow path loop. And this is a situation where we call it topological. Okay, and similarly, this is also a case where it's topological, where if you look at this hand, it rotates twice, right? So now you see the pattern. As long as it winds by integer times, it's topological, where that integer is not zero. Moreover, if you stare at these clocks, it can only wind integer times. Can it wind 2.5 times, for instance? In that case, it means that if you stare at this clock, in this last step, it rotates by a lot, right? It rotates by a lot and such that it's pointing downwards. Can that happen? The answer is no. And the reason is very simple. It's really just because electrons cannot carry two clocks. You're only allowed to carry one. So when you go back to the same position, you cannot force this guy to carry two clocks. It's going back, and so it has to carry the same clock. So 0 times is fine, but it can only be integer times. Okay, so it's because of this reason that the Hall conductivity, Hall resistance is 1 over how many times of electron clock winds times some unit. Okay, so this result is shown by these people. And I'm not explaining that here because it's more mathematically heavy. So, so this is what they shown. And so the gist is that what matters is how many times the electron's clock winds. If it winds C times, then it means that you're, let's put it this way. So for electrons at this magnitude of B field, it winds 3 times. For electrons at this strength of B field, it winds 2 times. So that's what it means. Okay, so after this discovery, theoretical discovery, there are more materials with windings was discovered. Okay, and these materials have a name. These materials with winding have a name that's called a topological material. And now you know why. Because the definition of how many times it winds, as long as it's not 0, is that's defined as topological. Okay, and so actually this is the end of my talk. So the take-home message is there's this remarkable experimental discovery of Hall effect that it shows that the Hall resistance have this kind of step-like feature that's universal across different materials and all the details. And that number is given by how many times the electron's clock winds. Okay, so that's all I have to say. So I can take any questions that you may have.